look at these questions in exercise 3. The first one, consider a relation about people in the United States, including their name, social security number, street address, city, state, zip code, area code, and phone number. Okay, from this sentence, we know there is a relation. There is a relation. We can name it person. Okay, and there are some attributes. Name, access number, street address, city, state, zip code, area code, and phone number. And based on the following facts, the facts the database requirement, and based on this requirement, give FDs. Okay, and now let's look at these facts. An area code cannot straddle two cities. So that means if we're given a area code, the city is concerned. So then it means that if there are two tuples with same value on area code, they must have same value in city. But maybe you can write you're right. Maybe you write FDs like this: area code functionally determining city. But this city is the city name. In the relation, city means city name. But city, and from the sixth facts, we know two cities may have same name, so a name cannot identify a city. But two cities cannot have the same name in state. Then this means state and city, state name and city name identify state and city identify a city. So that means it's not just city name and state identify a city. So now we can get area code functionally determine city, state together. These two attributes identify a city. Okay, now next one. A zip code cannot straddle two area code. Then we know zip code functionally determine area code. Then if any two tuples with same value in zip code, then this address must be in a area, in one area. So they have same value on area code. Okay, now two people cannot have same society security number. Then this means access number identify a person. From here we can get these facts. And now here, But we cannot find a fact like this. Uh, two persons cannot have the same name. Because in China, after I said in China, many people have same name, So in China, a name does not identify a person. Name does not identify in China, and I think in United States, name does not I identify a person. Okay, the sad facts fact. Two people may live in a same address, while a people can have only one address. When from this fact, we can assert two. Now we assert that let's assert two facts. Two FDs. The first one is SS number functionally determine address including state, city, and street. Okay, this is the first one. SS number functionally determine state, city, street. Does it hold? A person can have only one. Then, if any two tuples with same value on SS number, then means these two tuples is about one person. One person. This person and a person have only one. So, only one state, one city, one street. Then this FD holds. And let's assert another one. Street, state, city, street. Functionally determine SS number. Does it hold? Okay, now let's look at this one. This fact. Two two people may live in a same address. So that means if any two tuples with same address, same state, same city, and same street, maybe, but maybe, but it means the same. These tuples is about one address, but in one address there may be two persons, So we cannot say the component on SS number are same. So this FD does not hold. Now we can get this one. Okay, two people may have a same phone number, and a person may have more than one phone number. Okay, phone number. Phone functionally determine SS number. Does it hold? Two people may have same phone number. Then this means if any two tuples with same value on phone means they have same phone number, but there may be two persons. So the component on SS number maybe not be same. So it doesn't hold. Then SS number functionally determine phone. A people may have more than one phone. So this FD does not hold. A person may have more than one phone. So in this, the component on this is can be not same. Okay. And the next one, an address have only one zip code. Address includes state, city, and street. Have only one zip code, so this FD holds. People have only one name. People is identified by SS number, so SS number functionally determine name. Okay, now we can get these FDs. Area code functionally determines city, state. Zip code functionally determines area code. SS number functionally determines street, city. And state, city, street functionally determine zip code. And SS number functionally determine A. Now, based on this FD, what are the keys? What are the keys? And let's look at this SS number. Let's compute the closure of SS number first. Because we know if SS number functionally determine name, SS number and SS number functionally determine state, street, city functionally zip code functionally determine area code. It seems that SS number is very important. SS number, the closure of SS number must be very large. Okay, now let's compute it. Because the basis is SS number. SS number functionally determines state, street, city. Okay, state, city, street. And this SS number functionally determine name. And as state, city, street functionally determine zip code. Okay, now zip code is added. Zip code functionally determine area code. Area code is added. Area code functionally determines city, state already be here. Okay, now this is the closure of SS number. Let's check it. Name, ready in it. Accent number in it. Street, yes. City, in here. State, okay. Zip code, here. Area code, here. But no phone in the closure. No phone in the closure. So SS number, is SS number a key? No, it's not a key. It's not a key. It's not a super key because the closure of SS number is not the set of all attributes. No phone in the result. So what is the key? We can add phone in the closure in the set. Now, if we compute the closure of SS number and phone, we'll get all the attributes. So SS number phone is the key. What is the key? SS number phone. Now the second question. Suppose R is a relation with attribute A1, A2, A, and then it means R has n attributes. As a function of n, tell how many superkeys R has if the only key is A1. The only key is A1, then we know a superkey is a superset of a key. Then because there is the A1 is the only key, so the superkey is a superset of A1. Superset of A1 is a superset. And A1, A2 is a superset. A1, A3 is a superset. You can choose one attribute from A2 to AN. Then this attribute with A1 as the as a super key. Okay, so this is A1 is one super key, and choose a super key. Choose an attribute from A2 to AN. Then is choose one from m minus 1 attributes. And A1, A2, A3 is also an attribute. A1, A2, A4 is also an attribute. Okay, then the number of super keys with 3 attributes have choose two attributes from A2 to AN. So this is the number. And the super keys with 4 attributes, choose 3 attributes from A2 to AN. And so on. Choose AN minus 1 attributes from A2 to AN. Okay, and this answer is okay. This is the first one. Now, if the only keys are A1 and A2, if the only keys are A1 and A2, we can compute the number, the super keys including A1. The super keys including A1, we already computed. And the number of the super keys including A2 is also this one, this number. And because there is some super keys including both A1 and A2, this super keys is included in this number, this part, and this part, included in both this part and this part. So we'll minus it. Minus the supers including A1 and A2. including A1 and A2. That means we'll choose one attribute from A3 to AN. And then there are n minus 2 attributes. To select 3 and so on. Select all these n minus 2 attributes. Then this part is, then we can get this is B and C. The only keys are A1, A2, and A3, A4. Okay, then we can find the attributes, compute the number of the super keys including A1 and A2. And the number of the super keys including A3, A4. And we'll minus the number of the attributes including A1, A2, A3, and A4, because this superset is counted in both this part and this part, so we'll minus it. Then and now we can compute and yes. For the last question, consider the relation with schema R, A, B, C, D, and FDs. A functionally determine C, C functionally determine D, and D functionally determine A. What are all the keys of R? What are all the keys of R? And if we want to find all the keys of a relation, we can compute the all possible the closure of all possible combination of attributes. And now so you can compute the closure of A, the closure of B, the closure of C, the closure of D, the closure of AB, and the closure of BC, the closure of CD, and so on. But if we look at these FDs, let's check these FDs, we can find in the right side C, D, A. No B in the right side, so B must be in the key. Must be in the key. So if we want to find keys, we can just compute the combination including B, the closure of B. Now let's compute the closure of B. The basis is B. B, the closure of B is B. So B is not the key. Now let's add an attribute in it. AB, BC, and BD. Now let's compute it. AB. AB, the closure, the basis of a closure of AB is AB. And because A functional determine C is added, C functional determine D, so D is also added. And so the closure of AB is A, B, C, D. Now we know AB is a key. Now let's compute BC. BC, the basis is BC. BC, C functional determine D, so D is added. D functional determine A, so E is also added. A, B, C, D, so BC is also a key. And the closure of BC, BD. Now the closure of BD, BD The basis is BD. BD, D functional determine A, so A added. A functional determine C, so C added is added. A, B, C, D. All the attributes. So BD is also a key. Okay, now we already find the keys. And because A, B, B, C, B, D are all the keys, so we needn't compute the closure with 3 attributes. Needn't. All the ACD, the closure of CD must be ACD. It's not a super key, and all the other set of a set with 3 attributes, including B. So they are super key. They are super key. So now, what are all the super keys for R that are not keys? Super keys, supersets of key. Now, AB, the superset of AB, ABC, ABD, ABCD. Now, the superset of BC, BC, ABC already here. Now, BCD, BCD, and ABCD. Okay, now the superset of the supersets or a superset of BD, BD, ABD already here, BCD already here, BCD already here. Okay, they are the super keys of R that are not keys. Okay, now let's compute the closure of A. The closure of A, the base is A. And because A functional determines C, C is added. C functional determines D, D is added. D functional determines A already in the closure. Okay, no new attributes can be added. So the closure of A is ACD. Does C functional determinacy follow from the given FD? Now, if we want to answer this, we can compute the closure of the left side, the C. The closure of C is the base. C functional determine D, D is added. D functional determine A is added. That's all. So let's check the closure of C, A in the closure. So A functional determine A, the C functional determine A follows from the given FDs. And because B is not in the closure, so C functional determine D does not follow from the given FD.